Hey everyone, let us begin today not with what we think we understand, but with what keeps repeating itself in the data. As new observations of the interstellar Comet 3 I-Atlas continue to arrive, a pattern is emerging that refuses to fade with distance, time, or changing geometry. According to two recent analyses by Avi Loeb, this object is not only producing a persistent sunward jet, but its rotation axis appears aligned with that same direction even at large distances from the sun. At the same time, the anti-tail itself remains unusually narrow and tightly collimated. Together, these observations raise important questions about how this comet is structured and how it releases material into space. To understand why this alignment matters, we need to start with what normally happens. In typical solar system comets, rotation axes are essentially random. They are shaped by chaotic collisions, uneven outgassing, and long histories of thermal stress. As a result, jets often sweep across the sky as the nucleus rotates, producing broad fans or changing tail orientations over time. A sustained alignment between a comet's rotation axis and the direction toward the sun is not something we usually expect, especially when the object is still far from perihelion. In the case of 3I Atlas, the situation appears different. Observations indicate that the axis around which the comet rotates remains closely aligned with the sunward direction even at large heliocentric distances. This means that the same region of the nucleus continues to face the sun over extended periods. Such behavior suggests either a highly unusual rotational state or an internal structure that resists the normal torques expected from uneven outgassing. This becomes even more intriguing when paired with the nature of the anti-tail itself. Instead of spreading outward like a diffuse dust feature, the sunward jet of 3I Atlas remains tightly collimated. In simple terms, the material does not fan out. It stays narrow, focused, and sharply defined over enormous distances. In most comets, dust grains quickly disperse once they leave the nucleus, pushed apart by radiation pressure and interactions with the solar wind. A jet that remains narrow implies a sustained and highly directional release mechanism. One possible explanation is that the nucleus contains a confined active region such as a vent or fracture that channels material outward along a specific direction. If this vent happens to lie close to the rotation axis, then as the comet spins, the jet would remain stable rather than sweeping across space. This configuration would naturally produce a narrow, persistent feature that appears locked in place. While this is uncommon, it does not violate physics. It simply implies a level of internal organization not often seen in solar system comets. The alignment of the rotation axis with the sun also raises questions about how the comet responds to solar heating. Normally, uneven heating produces torques that gradually alter a comet's spin state. Over time, this leads to tumbling or changes in axis orientation. For 3I Atlas, the apparent stability of the alignment suggests either that these torques are unusually balanced or that the comet's internal mass distribution dampens rotational changes. This could occur if the nucleus is more cohesive or layered than typical cometary bodies. Another factor to consider is non-gravitational acceleration. Even small sustained thrust from outgassing can influence a comet's trajectory and rotation. If material is being released in a highly directional way, aligned with the sun, it could both produce the observed jet and reinforce the alignment of the rotation axis. In this sense, the jet would not just be a consequence of rotation, but an active participant in maintaining the comet's orientation. The tight collimation of the anti-tail also places constraints on particle size and composition. Very small dust grains tend to spread quickly under radiation pressure. A narrow structure suggests either larger particles, denser aggregates, or particles that evaporate rapidly after release. Interstellar comets are expected to contain unfamiliar mixtures of ices and dust, shaped by environments different from our own. If 3I Atlas formed around a star with a different radiation field or disk chemistry, its material properties could differ significantly from what we are used to seeing. It is important to emphasize that none of this implies anything unnatural. Alignment collimation, and persistence are properties that can emerge naturally under the right conditions. What makes 3i Atlas noteworthy is not that it breaks physical laws, but that it occupies a region of parameter space we have barely explored. With only a handful of interstellar objects observed so far, every new behavior expands our understanding of what is possible. The fact that these features are detected at large distances is especially valuable. Far from the sun, activity levels are lower, and simple explanations based on intense heating are less applicable. Seeing a stable, sunward aligned jet under these conditions suggests that the driving mechanism is efficient and well organized. As the comet moves closer, this behavior does not disappear, reinforcing the idea that it is intrinsic rather than transient. Another point raised by Avi Loeb's discussion is the consistency of the observations. Independent datasets, different instruments, and different observing campaigns all point to the same basic geometry. This consistency matters. It reduces the likelihood that the alignment or collimation is an artifact of processing or perspective. Instead, it points toward a real physical configuration that persists across time. From a broader perspective, these observations highlight why interstellar comets are so scientifically valuable. Objects formed around other stars offer natural experiments in planetary system diversity. They show us how different initial conditions can lead to different outcomes, even under the same physical laws. 3i Atlas is not just another comet with a few quirks. It is a data point from outside our solar system, carrying information about environments we cannot otherwise sample directly. As 3i Atlas continues its outbound journey, opportunities to study these features will gradually diminish. Activity will decline, the jet will fade, and the geometry will become harder to measure. That makes the current observations particularly important. They capture a moment when the comet is active enough to reveal its internal behavior, yet distant enough that subtle effects are not overwhelmed by intense solar heating. In the end, the alignment of the rotation axis with the sun and the tight collimation of the anti-tail point toward a comet that is structurally organized in a way we do not often see. This does not require extraordinary explanations, but it does require careful attention. Anomalies like these are not problems to be ignored. They are opportunities to refine our models and broaden our expectations. 3i Atlas continues to remind us that our understanding of comets is shaped by a very small sample. Each interstellar visitor adds another piece to the puzzle, showing us that nature is capable of producing outcomes that look unusual simply because we have not encountered them before. The real value lies in documenting these behaviors honestly and letting the data guide our conclusions wherever they may lead.